Hello, my name is Brandon Weekly, and today we're going to be covering the Attestation use case enabled by our CEC1736 Platform Root of Trust controller. We'll start by defining attestation and giving some background and details on it so that we can understand what kind of value it adds to our system in terms of security. Then we'll show how you can provision this use case using our Trust Platform Design Suite software. You can download this software for free from the link in the description, and check out the other videos in our YouTube playlist to learn more about other use cases enabled by TPDS. We'll start with the obvious question of what is attestation? To give the technical definition, attestation is the mechanism by which an authority in the system verifies the authenticity and integrity of the hardware and software of a device. The basic idea is that we want to be able to ask a given device in a system for its identity and information about what it's doing, which it will then sign with a private key that only it could possibly have access to. Two terms to keep in mind when talking about attestation are attestation verification, which is the authority that describes the device's configuration. Again, what is it doing and is it authorized to be doing that activity? And attestation evidence, which is what we use to prove that the device is what it says it is. So what can this use case do for the security of your platform? Well, virtually all modern systems are comprised of devices that are built all over the world. So during your manufacturing process, you're going to have components shipped from one place to another many times before the end product actually ends up in the customer's hands. This can potentially open you up to what we call a supply chain attack, where somebody swaps out components for counterfeit ones or does something else while the platform is in transit to compromise it in some way. Attestation allows us to make sure that each individual component inside of that system can uniquely identify itself, even versus another chip of the exact same CPN. It can uniquely identify itself so that we're sure that that is the one specific part that is intended to be in that socket. So this will help us prevent supply chain attacks, and it will help it once it's in the field to make sure something similar doesn't happen where somebody doesn't swap it out for a similar device that, again, it does something malicious. Now, naturally, you may ask, how does this work? How can a device uniquely identify itself against an exact clone or even an identical device that comes from the same manufacturer? And the answer is a physically unclonable function, or a PUF. We'll cover this technology at a high level here, but we'll provide some links in the description that cover it in more detail. Now, the premise is that any application processor, any microcontroller, and certainly the CEC1736 are comprised of millions to billions of individual transistors. And for the purposes of digital logic, these transistors act like little switches. They'll be switching on or off constantly throughout their use. This is where binary is derived from. Is the transistor a 1 or a 0? Is power going through it, or is it not? Now, when the device is powered down, each of these individual transistors will revert to something of a neutral state. And these states will vary from one transistor to the next, to the point where when you add up all of these micro variations, you can extract something of a digital fingerprint from this device, or from the SRAM when we're talking specifically about the CEC1736. When it is powered off, you add up all these micro variations and you have a unique device identity that you can derive that cannot be duplicated by, again, a clone or any other CEC1736 that comes from Microchip. This fingerprint is unique to this specific device. Once we've measured this device fingerprint, we can use it to derive a private key that will be unique to the device that's utilizing the PUF technology. Again, the culmination of all the micro variations of the transistors across an entire device can't be replicated by even an identical device, so the key that we generate will be unfalsifiable. And the beauty of it is we don't have to store it anywhere, so it's in no danger of being extracted from the device somehow. We can simply derive the key when it's needed, and then it's gone once it's done. Now, what this might look like in practice is you will have maybe the application processor, maybe some other device that's meant to be the attestation requester. And what that will do is send out a request to a device for it to attest itself. And what the CEC1736 does is it will generate its private key, as we explained, from its SRAM PUF, and it will then use that private key to sign the response to the attestation requester, and then sends it back. If this signature is considered valid, we will then have passed the attestation request and it will be allowed to operate as intended. Now we're going to jump into a demo of the TrustFLEX variant of the Attestation configurator for the CEC1736 in Trust Platform Design Suite. But before we do that, here is a list of things that you'll need to follow along with that demo, and then generate your own provisioning package to configure your platform for Attestation. Now, the first thing you'll need is a laptop or a PC that's running either Windows or a Linux operating system. Next, you'll need the CEC1736 development board. This comes fitted with a socket that allows you to swap out the CEC1736 chip. This is important because it has a one-time programmable block on it, and several of the fields in Attestation utilize this OTP block. So if you burn it and need to try different configurations, you can simply swap out the part. Next, you'll need the latest version of Trust Platform Design Suite, and it shares some dependencies with MPLAB, so you'll need the MPLAB X integrated development environment as well. Now here I have Trust Platform Design Suite up and running, and I'm going to show you how to get to the CEC173X configurator and how to configure Attestation specifically. So here from the TPDS homepage, we'll come over to this Configurators tab and click on that. We'll come down and click on the CEC173X TrustFLEX configurator. This may take a moment to load, so I already have a tab open, but once it does load, you'll get a page that looks like this. We'll then come over to System Configuration in the top left. We'll scroll down and we'll find the list of use cases that are enabled by the CEC173X. We of course want to make sure that Attestation is checked. We'll then find it up here on the top left and we'll click on it there. And here we'll find the configurator for Attestation. It's a relatively simple one. It has two sections of information that will need to be filled out. This first section is the certificate settings. And we'll find here at the top the certificate base address, which is labeled as an OTP setting. Again, the OTP is a one-time programmable block in the CEC, so if you give it a certificate base address and want to try a different one, you will need to swap out the chip that's in your board. But this is where you're going to store your Attestation key certificates. Next, you'll decide on the types of certificates that you want to use of the two options we have here. And next, you will decide where your Attestation key is going to come from. As we've described it, it comes from the SRAM puff, but you do have the option of generating a key that is then stored in the OTP, and you can use that for Attestation. Next, we have our certificate chain settings. Another OTP setting, you have your HSM or hardware security module serial number. This is a tag that identifies your HSM. Next, we'll select what kinds, or rather which certificates you're going to use for Attestation. We'll select our certificate chains, and then we'll decide what slots they're going to be stored in the CEC. Now that is it for the settings that you need to configure, but you do have something of an educational piece up here that you can pop out of TPDS, and this is the transaction diagram that shows you what's going on when you're setting up Attestation and then what happens when the function is called upon in the field. There are a couple of components that are interacting to enable this feature, as we've already described, but we have our application owner, we have our application processor, we have the boot ROM that's inside the CEC173X, we have the EC firmware, the embedded controller firmware, which in the case of the CEC is our proprietary Soteria G3 firmware. You can learn more about that on our website. We have a Soteria G3 sell sheet that goes over not only Attestation, but also all of the other use cases that the CEC enables. We have the OTP, or one-time programmable block, as we've talked about. We have the internal flash of the CEC173X. Depending on the package you have, it's going to be either of 2 megabytes or 4 megabytes. And then we have the external flash, which typically houses the boot code for your application. Thank you for watching this Chiptorial episode covering Attestation with the CEC173X Platform Root of Trust Controller. Be sure to check out the description for more educational materials on PUF technology and Attestation, and for more information about the CEC173X. Also check out the other videos in the playlist to learn more about different use cases enabled by our Trust Platform Design Suite software. Thanks.